Hi, I'm J Wildberger, and today we're going to be looking at the group of blue planar isometries. So we're going to be investigating rotations and reflections in the ordinary Euclidean space with a view of how they compose. But before we do that, we have to have a look more carefully, especially at reflections today, at how to generate them, why they're called reflections, and we're going to derive some formulas that are going to be useful for us in the relativistic situation. So basically what we want to do is set things up so that we're actually in a position to work with the general bilinear form. Okay, so here are the formulas that we had that we're talking about: motions of the plane, grounded isometries. The point xy is sent by sigma AB to the product of the vector xy with this matrix A, B, B minus A. We call that a reflection for reasons we'll explain today. And the other one was the rho AB, which represented by this matrix here, A, B minus BA. So they're very close. The only difference is that the bottom row here is negated going from one to the other. And the point AB, very importantly, lies on the unit circle x squared plus y squared equals 1 for both of them. So for example, if let's say the point AB happens to be 3/5, 4/5, which say is right there, then we have these two transformations, and they look as follows. So the reflection, in this case, turns out to be a reflection in this line right here. So that would be like the sigma, okay? And that reflection would send that point to that point, send that point to that point, and so on. So in particular, it sends the point 1, 0 to the point 3/5, 4/5, which indexes the reflection. And the other one, the rho, will be a rotation, and it will be the rotation that takes the circle, or the entire plane actually, and moves it around so that this point is getting sent to that one, and this point is getting sent to that one. Everything is moving around by that much. Okay, so those are examples. Now we want to have a look at reflections and ultimately the composite structure when we compose them. So let's move towards this idea of understanding reflections in a vector u. Here's a vector u. We want to understand how to get at the transformation that takes a point here and sort of sends it to the mirror image on the other side of that vector, where the vector is centered at the origin. So in particular, the points on this line would be fixed. Okay, so to get at that, a stepping stone is to first talk about the projection of a vector onto another vector. In this case, the projection of the vector v onto the vector u that we're interested in. So there's the vector u in that direction, there's the vector v right there. And we want to know, what is the projection of the vector v onto u? And in the diagram, it's represented by this vector w. So this vector is the projection of the vector v onto the vector u. Now notice that the vectors v and u in this picture are oriented so that they're starting from the same point, in this case the origin. And what we're doing is we're perpendicularly going from the vector v's tip to the direction of the line generated by the vector u. Okay, and the formula for it is well known in linear algebra courses. It's an expression involving the vectors v and u, and naturally the dot product that's used to establish the perpendicularity. And here's the formula, that the projection of v onto u is, well, there's some multiple of u. Well, that's not a surprise because it's going to be a multiple of u. And the multiple is the quotient of v dot u over u dot u. v dot u divided by u dot u. So this will just be the quadrants of u. And that's our projection vector w. Now, why is it that formula and not something else? Well, let's check that this actually satisfies what we wanted to have, which is the property that if we take the difference between v and w, so v minus w, that would be that vector there, okay, that vector ought to be perpendicular to u. And the way we check perpendicularities, we take a dot product and see if something is 0. Okay, so what would happen if we took this w and looked at v minus w dot u? Well, by the bilinearity of the dot product, this is v dot u minus w dot u. And the w is this formula here, so we just replace it there. And then when we look at this expression dot u, this is a number. So the number pulls out front and we just end up with u dot u. So the u dot u that we get ends up simply canceling with the u dot u that's on the bottom there, conveniently. And we just end up getting v dot u from here minus v dot u from here. And so whatever v and u are, that's necessarily 0. And yes, indeed, the difference vector here is indeed perpendicular to u. So that justifies our assertion that this is the projection of v onto u. So this is a very important formula, and this argument is very pleasant because it only depends on the bilinear properties of the dot product. In particular, if we have a different kind of dot product, like a red one or a green one or a different one, this still is defining projection of v onto u. So now that we have the idea of the projection of v onto u, that vector w there, we can now talk about the reflection of v in u. Here's u, we're reflecting v in u, and that's this vector over here. Vector v gets reflected to v prime. And might give that a name, something like the projection. V prime is the reflection in u of v. Now, how are we going to get at this v prime? Well, it's going to be determined by the symmetry that you see in this diagram, that here's v and here's v prime, that the w that we've just found, the projection, should be exactly halfway between them. That's the reflective property. Or in terms of vectors, the average of v and v prime, so the sum divided by 2, ought to be w. This condition exactly captures the fact that v and v prime are on different sides of w, and the line that's joining them is indeed perpendicular to u. Well, this is easy to solve for v prime. V prime is then minus v plus 2w. And so then the formula that we get is that the reflection of v in u is minus v plus 2, and here's that w expression that is the projection, v dot u over u dot u times u. So it's a combination of v and u with coefficients minus 1 and this little number here. So this is a very general formula for the reflection of one vector in another vector. So now let's take that formula and look to see what it looks like in the blue geometry, the Euclidean geometry. So we're going to be specific. We're going to let u be the vector rs and v be the vector xy. So we're interested in the reflection of v in u. So we think of this as being fixed, and this one here is sort of variable. All right, so the formula is the reflection of v in u. It's minus v, so there's minus v, plus, there's some multiple of u, that's u there, and here is 2 times the dot product of u and v. Well, the dot product is r times x plus s times y. There's the dot product. Divided by the dot product of u with itself, which is r squared plus s squared. All right, so this is a vector. It's a combination of this vector and this vector. So its coordinates are going to be what? Well, the x-coordinate is going to be the x-coordinate here, which is minus x, and the x-coordinate here, which is just this number, 2rx plus sy over r squared plus s squared, times the x-coordinate here, which is r. And the y-coordinate of the whole thing is the y-coordinate here, which is minus y, plus, again, the same constant, times now just s. Okay, so now we simplify this a little bit. So there's an r squared plus s squared in the denominators here. So let's pull that out front to make it a little bit simpler. We'd have to get a common denominator here. So when we do that, what's going to be in this first expression after we've pulled out this denominator? Well, how many x's are there going to be? There's going to be minus r squared x and minus s squared x, And over here, there's going to be plus 2r squared x, for a total of r squared minus s squared times x. How many y's are there? Well, it's just 2rsy. Similarly, over here, the x term only has this thing here, so the coefficient would be 2rs. And how many y's? Well, there's some from here and here, so we have to take this thing and multiply by r squared plus s squared. This will be minus r squared minus s squared, there's coefficients there. And here we're going to get a 2s squared. So altogether we're going to get plus s squared minus r squared, or if we use the same expression, minus r squared minus s squared times y. Now that looks a little bit imposing until you sort of look at it and realize that the coefficients that are appearing here are in fact very familiar. Because we have an r squared minus s squared over r squared plus s squared, and that's occurring there and also over here. And the other one is 2rs over the same thing, and that's occurring here and here. So we can write the whole thing as xy times a, b, b minus a, where the a is r squared minus s squared over r squared plus s squared. The b, this one or that one, is going to be the 2rs over r squared plus s squared. So this first expression is a times x plus b times y. And the second expression is b times x minus a times y. So here's where we're getting the formula for the reflection that we wrote down. It's given by this matrix, a, b, b minus a, where the point AB does indeed lie on the unit circle, because we recognize this is the projective parametrization of the unit circle. It's the projective parametrization of the unit circle, and that's always a point on the unit circle. And so that's why we're getting this form of the reflection. We're just going through the formula for the reflection in general applied to the blue Euclidean geometry. So we've actually accomplished quite a good thing here. This is a topic which is rarely treated correctly in textbooks. So it's really valuable for you to understand fully what's happening in this situation here. It's obscured by the relatively sloppy treatment of modern mathematics with the number theoretical issues of the continuum and real numbers. So the reliance on real numbers causes one to be confused about what's really going on here. Okay, so adopting this purely rational point of view, what have we accomplished? Well, first of all, we're starting with a vector, u, which in this case is in the direction of rs. And we're describing the reflection in that line, okay? And what we've discovered is that this reflection in this line is given by a matrix exactly this form, a, b, b minus a, where the a and b depend on r and s in a very pleasant way. The a and b is just the point on the unit circle whose projective coordinates are r, s. And because this is the form for the matrix, it means that when you multiply by 1, 0, you're going to get the vector AB. So geometrically, the significance of this point AB is that it's the reflection of the point 1, 0 in the line that we're considering. So there's a correspondence here between the RS, so the data that specifies the line, and the AB, the actual point where the 1, 0 is reflected to, which actually is responsible for encoding the matrix for the transformation. And it's a little bit subtle. And one key property of this is that this expression is homogeneous in R and S. That means if we multiply the point RS by a scalar, so move it along this line, then this expression doesn't change. So if we call this expression ERS, then it's going to be constant if we multiply R and S by some non-zero scalar lambda. And this is, as I said, just the projective parameterization of the unit circle. So one thing that this accomplishes is that it explains how there's a correspondence between lines through the origin, because that's really all that's required here is the input. It's the line through the origin that's really the input, not exactly the vector. Because of this homogeneity, if you scale the vector, the transformation is not changing. So it's really only the line that's really the input. And the output is we're getting this point A, B on the unit circle. So there's a correspondence between lines through the origin and points on the unit circle. But it's this relatively subtle one that given the line, you get at the point by reflecting 1, 0 in that line. Now notice that this line does not necessarily have to meet the circle because we're not working over the real numbers. We're not just assuming that curves meet if it looks like they meet. Okay, it's always a number theoretical issue whether or not two curves meet, whether we like it or not. That's just the reality of it. So there may be an intersection point here of this line and the circle, and there may not be. Okay, but what there definitely is this point here. So this line does not determine a point, and if it did, it would actually determine two of them. But this line determines a unique point, which is that one there. So as this line goes all the way around, that point goes all the way around. You can sort of see that. Imagine this line as it's going all the way through the full range. There's the full range of lines. The point is going twice as fast. Right. So it's a one-to-one correspondence, a bijection if you like. Okay, this is also very pleasantly connected with the arithmetic of complex numbers. So here's a little exercise that allows you to play around and think about that. So show that if this point RS that we're choosing here is identified with the complex number R plus IS, so imagine this is the complex plane for a second. Let's call that complex number Z. Then you can show that the point AB, or as a complex number A plus IB, is just what you get when you take this complex number Z and you square it and then you divide by its quadrants. The quadrants is Z times Z bar, or the sum of the R squared plus S squared. So I want to consider a special case of that last picture, which leads to a famous trick in calculus called the Weierstrass substitution, which is used to help us integrate functions involving cosine and sines. Okay, so a lot of stuff that I'm going to say on this page has quotes around it because whenever you're talking about angles, there's a serious risk that you're not talking about something that's properly defined. And in a similar way, cosine and sine involving infinite series, they're actually computationally highly dubious things that you can only get at approximately. So nevertheless, still I want to connect with a standard trick or a technique in sort of an advanced calculus class that goes back to the 19th century mathematician Carl Weierstrass. So the special case is when we're considering our point RS to have a rather special form. Let's consider the point RS to have x-coordinate 1. So instead of RS, we'd have 1h. That means that our point will lie on this line, x equals 1. Let's put it right there. So that's the point 1h. Well, in that case, this point E1h, which is the reflection of 1, 0 in the line over there, turns out to be just what we call E of h in terms of the rational parameterization of the circle. We just get 1 minus h squared over 1 plus h squared and 2h over 1 plus h squared. Right? So instead of having r's and s's, we now have 1 and h's. So instead of r squared minus s squared, we can have 1 minus h squared, 1 plus h squared, 2h, 1 plus h squared. And this is the familiar rational parameterization of the circle that I go on and on about as being very important. So we're touching base with this rational parameterization. which is just a little bit less sophisticated than the projective one, by restricting our point to lie on this line. So that means that this line here that we're talking about cannot quite go through the full range of motion. So we can get any line that we like in this direction, except for the vertical line. That one we can't get. And that's the reason why we can't get at this point over here, because it's not included in the rational parameterization. Okay, so now where does this Weierstrass substitution come in? Well, this is a point on the unit circle. And in the usual story, it can be described in terms of cosine theta and sine theta, where theta is an angle in quotes. Cosine theta in quotes, sine theta in quotes. Okay, so there's the angle theta that's usually drawn very confidently in traditional stories, even though, in fact, actually calculating such a thing is almost always impossible. But nevertheless, that's the story that's usually taught. So there's an angle theta from the positive x-axis to this direction towards this point on the circle. Now, if we look at the geometry of the story here, when we've said that this point is reflected in this line to this point, this line is perpendicular here, that's going to mean that this line is bisecting this angle here. So that's theta all the way there. Then each of these smaller halves is going to be theta over 2. And also, this angle over here, the same angle that subtends an angle of theta at the center, will subtend an angle of theta over 2 at the circumference. That's a familiar kind of fact of classical circle geometry. So that's theta over 2. And that tells us actually that this line and this line are going to be parallel, because that's theta over 2 and that's also theta over 2. Well, that's parallel to this. This is just 1 over. So that means that where this line meets this line and where this line meets this line, it's just going to be 1 over. It means that this point here is going to be 0h. So that's simply reinforcing what we already know, that this point E of h with rational parameterization can be obtained from the point -1, 0 by drawing a line to where it meets the point on the y-axis with coordinate h. So this diagram very pleasantly shows us that if we didn't know that these angles were the same, we now would have a demonstration that those angles are the same, because these lines are necessarily parallel. Okay, so where does the substitution come in? Well, it's a consequence of the fact that there's a direct relationship between this number h, which is figuring here, and this angle theta over 2. And you can see it in either of the diagrams. So let's say with this triangle here, this side is 1, this side is h, and this angle here is theta over 2. So that means that the tangent of that angle, which is sort of opposite over adjacent, will be h over 1. In other words, just h. So tan of theta over 2 is h. And so this is the substitution. So the story is that you have some complicated integral, perhaps, that you want to simplify. You want to so-called rationalize it. Then what you do is you get rid of the angles. You get rid of the angles by replacing the theta with h. And this is the relationship between the theta and h that you're going to use to do the replacement. So if these are related this way, then this diagram here shows that the cosine theta and sine theta are just this expression and this expression. In other words, you make this substitution, then cos theta can be replaced with 1 minus h squared over 1 plus h squared, or in this case 1 minus t squared over 1 plus t squared. And the sine theta can be replaced with 2t over 1 plus t squared. And then if you analyze this a little bit with classical calculus, you can convince yourself that the d theta is replaced with this differential 2 dt over 1 plus t squared. So This has sometimes been called the world's trickiest substitution. It is quite clever, and undergraduates who learn it often, so it's just like a rabbit out of a hat, but it's really all happening as a consequence of the geometry of this diagram, and in particular the relationship between this quantity h and this point e of h over here. Now in our algebraic calculus course we talk about that, and this quantity h is called the half slope of this point, or more precisely the half slope between this vector and this vector. And you can kind of see why that's not an unreasonable definition perhaps, because we're sort of going halfway and then we're looking at the slope. Okay, so that's quite pleasant, and it turns out that well, basically a very similar kind of story will be able to be presented when we go to the relativistic version of things. So the situation is so general that it extends naturally to the red and green geometries too in very interesting fashions. All right, so now that we're experts on reflections, we can get at the group structure, the composition of reflections pretty easily, because it's just a little bit of linear algebra. So suppose that we have two reflections, sigma AB and sigma CD, corresponding to 2 points on the unit circle. Then the corresponding matrices are given by these, AB, B minus A, and CD, D minus C. And when we multiply those two matrices, we get AC plus BD, AD minus BC, CB minus AD, and BD plus AC, or AC plus BD. And this is not a reflection anymore. It's not of this form because this term is the same as that term, and these ones are negatives of each other. So this is a rotation matrix, so a row kind of matrix that we talked about at the beginning. In fact, it's row of AC plus BD, comma, AD minus BC. This is telling us how to combine one reflection with another reflection to get a composite rotation. And as a little exercise, if you like, you can check that another way of saying this in terms of the corresponding half slopes, or these parameters, the rational parameters, say h and k for these numbers on the unit circle, that's sigma of e of h followed by sigma of e of k is rho of e of this number, k minus h over 1 plus kh. So that's how the composition looks like at the level of the rational parameterizations. All right, so that's a good start to the story. We've understood reflections. Now we would like to understand rotations, the larger picture. So then we have the isometries, at least the grounded ones, comprised of both reflections and rotations, forming this very nice group structure. And that'll really set us up for doing a very similar kind of thing in the relativistic situations, where things become much less familiar. So I hope you'll join me for that. I'm J Wildberger. Thanks for listening.